My name is Jager, and I'll be going over system testing, along with my group mates Brian, Patrick, and Victoria. First thing I'm going to talk about is the Unix philosophy. Unix philosophy, summed up in a quote by Doug McElroy, a former head of Bell Labs back in the 1960s, said, "Write programs that do one thing and do it well. Write programs to work together. Write programs to handle text streams, because that's the universal interface." This talks about keeping programs as simple as needed. Along with the Unix philosophy, a person named Eric Raymond came up with 17 rules in his book on the subject that I will go through briefly. Modularity divides the code up into modules to keep problems local and easily identifiable. Clarity means using comments and variable names that make sense and other things to keep the code readable and clear. Composition means instead of one large program, you should break programs into small chunks and then call those chunks separately to work together. Separation involves keeping the front end and back end parts of the program separate. Simplicity is involved with writing many simple chunks of code rather than one complex block of code. Keep it as simple as possible. Parsimony refers to the economic term parsimony, where it is much harder to get rid and add big things rather than small things. So keep your code in small pieces so that adding and deleting is easier resource-wise. Transparency means making required input and output formats very visible to future developers so they can tell what exactly is needed by the program and what output the program should have. Robustness, we talked about this in our essay, so I'm sure everyone's familiar with the concept, but it makes your code more maintainable. Representation, when deciding in your program between making the data of the program complicated or the logic, you should choose to complicate the data, because it's easier to explain complicated data than it is to explain complicated code logic. The rule of least surprise means that programs should behave how a user would expect them to behave. The example of a calculator program, if you hit the plus button on your keyboard, you'd expect it to do the same thing as clicking an add button. And so, precepts that the user has about what they expect to happen should be what actually happens. Silence, a program should only print out what is needed. Repair, if a program is designed at some point where it could possibly make an error, make it so that it is a very loud error, meaning that it either disrupts a lot of the program or is caught by error handling, because subtle bugs that accumulate are much worse than catching an error early on and fixing it. For economy, it is important to reduce development costs by valuing developer time over machine time. It is very cheap to use a machine to do something rather than a developer, so if possible, if you need to increase either machine time or developer time, always go to machine time. Generation, if code can be generated by a high-level program, you should do that rather than writing by hand to avoid human error. Optimization, you should prototype to avoid costs later. Diversity, programs should be able to be easily modified. And extensibility, programs should be designed so they can be expanded upon. Having these two kind of work together, have them easily modified and expanded upon, it makes your program much more powerful in the hands of other developers. Causes of faults during development. The table on the right shows all the causes of faults during development. You can see with the arrows on the graph that many of these faults can show up in two different stages. this can kind of make it hard to determine where the fault came from, but which can lead to tricky things in software engineering. I'm going to go over the testing process. System testing, the purpose of it is to verify, validate, and ensure that a system functions in all environments. The 4 stages are shown below: the function test, performance test, acceptance test, and installation test, usually in that order. The function test should check whether the system meets functional requirements. The performance test should make sure that the system performs to the standards needed by either the customer or the system designer. The acceptance test means that the customer should be able to accept the product that's given to them. And the installation test should test to see if once you install the system in its environment, if it still works or has any other bugs that weren't accounted for. For an example of an AC unit, a function test would be, like a program for the AC unit, does the program properly cool? A performance test could be, how long does it take for the system to cool? The acceptance test would be, does this system work within the requirements of the customer, whoever is purchasing this AC program? And the installation test would be, once you put the system out in, say, example, the floor to heat, will it withstand the new environment? Configuration management is what I'll be talking about next. Configuration management is concerned with how different versions and releases of a product are taken into account. The version and releases are often used interchangeably, but usually releases refer to a different form of a product, but still the same product, whereas versions can differ a little bit more generally. Regression testing is a good way to test new versions with previous versions by making sure they perform the same tasks as before. If they don't perform the same tasks as before, the system can often be seen as a downgrade and can lead to a lot of problems. For example, a calculator program that, say, we're adding in the new version to use powers of E, we need to make sure that this new powers of E does not affect using other powers, such as powers of 10. One way to keep track of version control is version control systems. They implement, or it's implemented directly integrated with 4 major capabilities. It stores all the objects that it needs. It has all the different configurations. It has a make facility where you can choose a bunch of different objects and combine them to one. And then from those you can construct a specific version of the software. It's a great way to organize your different objects and create different versions and keep track of what aspects certain versions have. It's a very useful tool for software developers. Similar to the version control system is a change control system. The main difference, instead of keeping multiple different versions, you keep only a couple versions and just monitor the changes made. You need to monitor the changes made because if you want to get back to an old version because a change is bad, then you can easily undo if you have the steps written down.
The next topic we'll be going over is the test team. You have the QA lead, plans budget and schedule, represents the testing team, and synchronizing testing process with development. A team lead implements the test process, assists testing team with new testing techniques, and validates quality of testing. Our usability test engineer designs and administers usability testing. The manual testing engineer uses test data to develop test cases. Automated test engineer uses test tools to execute tests. And the network test engineer tests the network and the database. The test library and configuration specialist manages test script changes and maintains the test script versions. The tester conducts testing according to set standards and analyzes test results and submits reports to the development team. And all these team members must uphold proper test documentation. The cause and effect graph. The cause and effect graph shows connections between outcomes and their dependencies. Causes represent the input conditions and effects represent the output conditions. Lines between the nodes represent a connection. These connections can be negated, and they can be grouped to perform logical operators as shown in the figure on the right. Here's an example of an ATM cause and effect graph. As you can see, if the machine is going to reject a card, its dependency is if the bank card is valid, negated. So if the bank card is not valid, it will reject the card. And if you want to pay money, you have to check first if there's money available, if the PIN is correct, and if the bank card is valid. All three of those dependencies get grouped and a logical AND is performed on them. Performance testing. Types of testing. We have performance testing determines response times, throughput, and resource utilization. Capacity testing. How many users can the system handle? Load testing. Tests if the system can perform well under normal and peak number of users/transactions. Volume testing. Database tests to verify the system can handle large amounts of data. Stress testing. Test the system behavior over designed load. Soak testing. Test performance over a period of time with high load. And spike testing. Test performance after a sudden increase in load. We also have reliability testing is used to find how often the system is failing in order to narrow down the main cause. We can measure this in terms of these three variables: mean time to failure, the average time between two failures; mean time to repair, the average time to repair the failures; and the mean time between failures, which is the mean time to failure plus the mean time to repair. Failure data. Interfailure times are the times between successful failures. The goal is to have higher time between failures over time, so the graphs will have an increasing trend over time, as you can see in this graph. We also have two types of uncertainties. Type 1 uncertainty is based on the fact that we never are sure the exact inputs or the order they are entered, and this can lead to some special case situations causing the system to fail unexpectedly. Type 2 uncertainty is when we try to fix an issue that was previously causing failures. We do not know whether the fix will be completely successful, and other issues could come up as a result, or the same issue could still be there for special cases. These uncertainties can be represented in the graph as the downturns in the graph. Since we want an always increasing graph, the downturns can be our uncertainty.
Alright, I will be talking about quality measures. Three types of quality measures are reliability, availability, and maintainability. In terms of a real scenario, we'd take a look at your car. Your car is reliable if it has long periods of consistent, desirable behavior between maintenance. Your car is available whenever you need to use it at any given time. And your car does not need maintenance. The maintainer can easily find parts for replacement. In terms of software, we want our software to perform correctly and consistently over long periods of time, to be reliable. We want our software to be available when we need it, and we want our software to be repaired easily and quickly should it fail for maintainability. In terms of an actual definition, software reliability is the probability that a system will operate without failure under given conditions for a given time interval. This is measured on a scale of 0 unreliable to 1 reliable. Reliability is measured over execution time, not real time, in order to more accurately reflect system usage. Reliability predictions are made using information of past failures and failure times, and this is done by analyzing the information provided and creating a predictive model. We can use any number of past failures to generate a model like the one below, and as you can see on this image, each line indicates the average of the last 2 failures. So for the gray, we have the average of the last 2 failures, and then an average of the last 10, and then the last 20. As we fix faults in software, our prediction model can be updated to reflect these solutions. More advanced models can reflect the type of solution with a weight, as some solutions are worth more in the area of reliability than others. Fenton and Flieger created a guideline stating any prediction system must include a prediction model that gives a full probability specification of the stochastic process. For example, functions f of t of I and the assumption of self-sufficiency of multiple times. An inference procedure for the unknown parameters of the model based on the values of t1, t2 through ti-1, and a prediction procedure that combines the prediction model and inference procedure to make predictions on future failure performance. System testing. Once all other testing has taken place, we begin acceptance testing, which is done by the users and customers. Acceptance testing enables these audiences to ensure that the system built meets all conditions and needs. Acceptance testing is done only by the users and customers and by developers when asked a technical question. There are 3 types of acceptance tests. There's a benchmark test, where the customer prepares a set of test cases that represent typical use of the product. There's a pilot test, which is when the system is temporarily installed but used in daily activity as if a permanent fixture. The customer will ask users to incorporate suggested functions in their typical daily procedure. And then there's a pilot test performed. If the pilot test is performed by developers, it's an alpha test, whereas a pilot test performed by customers, it's a beta test. Then we have a parallel test, is when the newer system operates in parallel with the old system. This allows users to become accustomed to the new version while also using the old, enabling an easy comparison of the 2 systems. Any one of the 3 tests above, or even all 3, can be used depending on the system and the customer's preference. Acceptance testing allows customers to truly understand what they want and what the users want. And going off of that, we look at this image on the right, we can see that acceptance tests are more of a business-facing test. This just means that it's for the customers and the users to really understand what they want and what they want their functionality to accomplish. The last testing is known as installation testing. Installation testing relates to installing the system at user sites. If acceptance testing were performed on-site, installation testing may not be needed. Also, if acceptance testing conditions were not the same as on-site conditions, additional testing may be required. To begin installation testing, we configure the system to the user environment, attach the correct number and kind of devices to the main processor, establish communication with other systems, and allocate files and assign access to appropriate functions and data. This test is done to verify the system is completely installed and that all functionality and non-functional characteristics work correctly under site conditions. For example, if we have a new ship, this ship should be using technology such as GPS, radar, communications, control systems, internet, etc. We would want these technologies to work no matter the site conditions such as stormy weather, the rocking motion of the ship, middle of nowhere, and fluctuating temperatures. Installation testing allows us to accomplish this. Automated testing is used to test a single component of a system, or maybe the whole system itself, without required devices connected to it. This is done by using a simulator. A simulator can be used to represent a device or system without having the device or system available. This is useful in scenarios such as if the hardware and software components are being built in parallel, if the testing location is off-site of the site location, or if messages are communicated or a database is accessed. The simulator can simulate these without replicating the entire database. Simulators give control over test conditions so that specific functionality can be tested. An example of this is if anybody has seen the movie Sully, it is based off of the real-life plane that crashed into the Hudson River. In order to see if the pilots made good decisions, simulators were used such as the one below, Basically, other pilots went in and were able to experience what happened and make decisions based off of that without actually being in a plane or up 30,000 feet in the air. Test documentation. Especially in regards to a large or complex software system, to control the complexity and difficulty of testing, we use complete and carefully designed test documentation. A test plan describes the system and the plan for testing all functionality and characteristics. A test specification describes each test and defines the criteria for evaluating each feature addressed. A test description presents the test data and procedures for the individual test. This includes a means of control, automated or not, data, and procedures. Test data is all data involved in the test, whether it's input commands, output states, messages, etc. A test script, or test procedure, gives a step-by-step description on how to perform a given test so that anybody could replicate it. The test report outlines the results of each test. It documents the results of a test, it provides info needed to duplicate any failures and to locate and fix errors, provides info necessary to determine if the project is complete. A fault report explains how a fault was found and fixed, and they are generally created in response to the filing of a discrepancy report form, which is filed when system outputs or behavior does not match expected output or behavior. This is an example. Test documentation will first start with the test plan. It'll go into the test specification test, which has requirements, functions, methods. Then the test description, which has the test data and procedures. And then the test is performed, and then a test analysis report is made.
Safety critical systems are those that which fail could result in human harm or loss of life, financial loss like property damage, or environmental damage. Some examples include aviation guidance systems, medical devices and monitors, military equipment, or scientific research equipment, for example, nuclear fusion testing. Design diversity is essentially the building of redundant components in a system, so that if one component fails, another component can take over. And this is to avoid system failures. And design diversity is often used in safety critical systems. Some examples include NASA's Space Shuttle general computers. They would have 4 redundant computers and 1 backup computer in case something went wrong. Another example would be operating room oxygen supplies. Standard practice is to have a main oxygen tank, a backup oxygen tank, and the wall supply system. Here's a figure of NASA's computer redundancy for the space shuttle. So, HAZOP and shard guide systems. HAZOP stands for Hazard and Operability. The main purpose of HAZOP is to study a complex process and figure out how it can fail and what damage it can cause when failing, and some ways to counteract that. SHARD stands for Software Hazard Analysis and Resolution and Design, and SHARD is essentially just an extension of HAZOP, but with a focus on software. Here's a figure of HAZOP guide words. Guide words are used to describe behaviors of a system. So for example, no means that no part of the intention is achieved. So for example, no forward flow when there should be. This is an example of a HAZOP matrix. At the top, it describes the purpose of each attribute, and at the bottom, it gives an example of how to use each attribute. So for example, the first entry is describing no cleaning agent, which means that the cleaning agent was missing during the cleaning cycle. And here's a more complex example of a shard matrix dealing with computer-assisted braking system software. So the clean room principle can be described by a NASA software engineering laboratory quote. After a programmer implements a function, the programmer must verify that the function meets its specification, rather than relying on unit testing to show that it apparently works. So essentially what the clean room principle is verifying the correctness of a function as it's written, rather than waiting until it's integrated to prove correctness. There are a few sub-principles to the clean room principle, including incremental development lifecycle, which breaks development into increments, and each increment is then tested on its own. Precise specification and design, which essentially compares the written implementation to the intended implementation. Statistical testing and software certification. It's impossible to test all possibilities, so tests are based on what's most likely to occur. Software reengineering is repurposing unclean software to be clean or to be correct. And then correctness verification is the verification of correctness as determined by the specifications of the original intent. To prove correctness, we look at control structures. Control structures are tested for correctness during each incremental step, for example, as each block or function is written. Control structures are essentially the building blocks of a program. Examples of control structures include sequences of code, if-then or if-else statements, and loops. And as mentioned earlier, correctness is based on the requirements of each function or block as they were planned. Here's a simple example of logic to determine what type of character is input. There are 4 possible classifications: an alphabetic character, numeric character, special, and other. And it helps to translate requirements into a mathematical function. On the left, we have a seemingly correct example of how to implement this logic. Each character is compared against a different classification, and then the type is assigned. On the right, it's an incorrect function because every character would be of type other since it's missing break statements. Here's further explanation of this idea. Essentially, we know that f of x is equal to y, so we just checked the logic to make sure that this is true every time. Proving correctness in programs is simple when you check the correctness of all the control structures. The reason why is because, as mentioned earlier, control structures make up the program. So if you check each piece of the program, the entire program will be correct. Here's an example of proving a program's correctness. So what we have is a function that's trying to determine the maximum of a number and an absolute value of another number. And the way we check this is we break it apart and verify each control structure separately in order of dependence. So for example, x should be verified before y if y is some function of x. And then once each piece is verified as correct, the program is then considered to be correct. Clean room efficiency. Verifying correctness as a program is being built increases efficiency. It reduces the amount of time needed for bug fixes or maintenance, allows for modularity in all programs regardless of the scale of the program, and each piece of the program can be worked on independently of one another. NASA performed a study on the efficiency of the clean room methodology, and they found that the design and code reading times increased greatly. And this is because programmers need to fully understand the functions that they write. NASA also found that code writing times decrease. There are significantly fewer errors. Less system testing is needed. And overall, there's a lower cost and a higher reliability of the project. Here are two pie chart comparisons between NASA's baseline effort and their clean room trial effort. On the left, you can see that they use more time and effort to code, a little bit more time to test, and less time to design. However, they spend less time reading and more time writing. With clean room, they spend more time in the design phase, less time overall in the code phase, but more of the coding is reading and verifying their code. And this figure shows more data collected from the NASA Clean Room study. On the left, it shows errors per delivered line of code. So on average, their baseline was about 7 errors, and the errors greatly reduced with the clean room trials. And on the right, their productivity is about the same or a little bit more. And here are some examples of some great system failures.